Types of Additive Manufacturing. These slides were developed by Rebecca Burton and Susan Arnold. The learning objectives for this module are to summarize the applied technology, the application to work and related work tasks, and build a process flow diagram linking work and work tasks to process, environment, and potential hazards. Additive manufacturing is broken into 7 categories. We'll take a closer look at each of the 7 categories, which include material extrusion, material jetting, binder jetting, powder bed fusion, directed energy deposition, vat photopolymerization, and sheet lamination. Material extrusion. In this technology, material is extruded through a nozzle or orifice onto the build platform. Like most AM, the product is built layer by layer. The feedstock for material extrusion is typically a solid filament, or pellets, composed of ABS or PLA. The polymer is heated to a temperature just above its glass transition temperature and extruded onto the platform. Fused deposition modeling is a trademarked variation of material extrusion that generally refers to industry-scale machines that are equipped with enclosed, heated build chambers. Fused filament fabrication is similar to fused deposition modeling, except fused filament fabrication generally refers to lower-cost desktop material extrusion printers. Tissue models constructed from cells using fused filament fabrication support medical research, pharmaceutical drug delivery, among other applications. Material extrusion major steps. The major process steps related to potential exposure to health hazards are pre-printing, during which polymer filaments or pellets are loaded into the printer, post-printing, during which the machine is open to retrieve parts, and post-processing, during which parts are polished using acetone vapor or chloroform vapor. Material extrusion materials. Feedstock materials used in material extrusion include acrylonitrile butadiene styrene, polylactic acid, acetone, or chloroform. These materials have the potential to evaporate when heated, and the contaminated air could be inhaled if the worker is exposed to it. Other hazards include hot surfaces, nip, pinch, or puncture of skin when interacting with the printer, and potential exposure to VOCs resulting from thermal degradation of the filament. With material jetting, hundreds of micronozzles are used to extrude a liquid resin onto a build platform. Dissolvable support materials, including waxes, gels, and wax polymer blends, are used in the printing. The resin is selectively cured using a UV laser. This process is repeated, building a product layer by layer. Major process steps related to potential exposure to health hazards include pre-printing, when the resin is loaded into containers, post-printing, when the part is removed from the build platform, and post-processing, when the parts are submerged into the batch to be washed. Materials used for material jetting include resins that are selected to impart specific colors and performance characteristics, such as flexibility and surface appearance, dissolvable support materials including waxes, gels, and wax polymer blends. Other hazards include UV radiation, thermal degradation products, surface contamination with resins, inks, support materials, and nip, pinch, puncture points. Binder jetting is a method wherein a liquid binder is selectively applied in the pattern of a layer of a product and then cured or sintered. Binder jetting is comprised of a powder reservoir and a build platform. The major process steps related to potential exposure to health hazards during pre-printing, the powders are loaded into the printer. A roller rolls a layer of powder from the reservoir onto the build platform, and the printhead applies one layer of binder, and then the binder is initially set by having an infrared lamp array pass over the top. The building platform then lowers, the level of powder in the reservoir is raised up, and the process repeats until all layers have been printed. This produces a green part, the part made of powder fused together with binder, submerged in a bed of unfused powder. This is an important feature of the method because it doesn't require any support materials to be integrated into the design, which is necessary for some other methods. During post-printing, the green part, in its box of powder, is placed in an oven, usually overnight, where the application of heat cures the binder enough that the green part can be handled without breaking. Next, it has to be removed from the bed of loose powder. This is usually done by digging the part out with a spoon or spatula of some kind, and then the harvest part is cleaned by having the loose powder blown off. This can be done in a glove box, something like a fume hood or a downdraft table, or simply out in the open, depending on the particle size of the loose powder. After that, the green part is generally sintered in a furnace to remove the binder and fuse the powder material into a finished part. Sometimes the voids created by elimination of the binder are backfilled with a secondary material, such as bronze. This is done post-processing. Feedstock materials for binder jetting include metal powders, mineral powders, binders, and cleaners. Powders, binder vapors that have evaporated from the heated binder or from cleaners, can be inhaled if the worker is exposed to the contaminated air. There is also the potential for dermal exposure from contact with surfaces that are contaminated with metal powders, binders, or cleaning agents. Other hazards associated with binder jetting include exposure to hot surfaces. This technology includes two main types of processes: selective laser melting and electron beam melting. For selective laser melting, a blade is used to spread a thin layer of powder across the platform that is then melted by reflecting a laser beam using a mirror. The process is repeated with the fresh layer of powder building the part layer by layer. Electron beam melting is, as the name suggests, an application in which the electron beam is used to melt the powder. This causes less residual stress compared to the electron beam melting, with less distortion, and as a result, the need for anchors and support structures is reduced. With this technology, the environment in the build chamber and AM machine must be blanketed with an inert gas to prevent feedstock powder oxidation. Major process steps related to potential exposure to health hazards associated with powder bed fusion include pre-printing, post-printing, and post-processing. During pre-printing, powders are weighed, mixed, and loaded into the printer. During post-printing, the printer doors are opened so that the part can be retrieved and depowdered. During post-printing, the printed part is cut away from the build platform and grinded to produce the final product. Materials used in powder bed fusion include metal powders, plastic powders, and powder blends. There is potential inhalation exposure to the powders that have become airborne. Similarly, powders that have settled on surfaces that a worker touches could lead to dermal exposure. Other hazards include hot surfaces, ionizing radiation, and pinch nip punctures. Directed energy deposition uses focused thermal energy produced by a laser or electron beam to fuse melted materials as they are deposited. The material is a metal powder or wire. This process produces near-net shape parts, meaning that the parts produced are very close to the desired final shape and size. This technique is attractive for its ability to reduce production costs and time associated with finishing steps. Unlike the other AM processes, with DED, multiple materials can be deposited simultaneously so that functionally graded parts can be made. Because of the 4 or 5 axis motion system that positions the deposition head, the process is not limited to horizontal layers, making it possible to repair existing parts. This process is also well suited to making large metal parts. Major process steps related to potential exposure to health hazards associated with directed energy deposition include pre-printing, during which wire or powders are loaded into the printer, post-printing, when doors are open so that the parts can be retrieved, and when the parts are cut away from the build platform. Finally, during post-processing, parts are machined to achieve final part dimensions. Major materials used in directed energy deposition include metal powders and metal wire. The use of ionizing and non-ionizing radiation sources also represent potential exposure risks. The use of nitrogen for creating an inert environment can also present an oxygen displacement risk. With vat photopolymerization, a solution of photosensitive monomers is exposed to a light source at the surface to cure those materials into a final object. The material undergoes a photochemical reaction, polymerizing it into a solid. In the case of photopolymerization printing, depending on the materials within the resin, you can get flexible, intricate parts or more ridged parts depending on the level of the plasticizer present in the solution. Once the UV light cures the part, there is excess resin left over in the vat, and the build tank or platform moves to accommodate building of the part layer by layer. The scope of types of parts that can be formed in photopolymerization printing is vast, and in fact many of the techniques used can create very small intricate parts, depending on the size of laser or light source. Major processing steps related to potential exposure to health hazards include pre-printing, when resins are mixed and dispensed into the vat, during post-printing, when the printer doors are opened to retrieve the part and cure it with UV radiation, and post-printing, during which the part is sanded and drilled. Materials used in vat photopolymerization include photopolymer resins, solvents, pigments or dyes, and other additives needed to achieve the desired product characteristics. These materials can evaporate and expose the worker via inhalation and contaminate work surfaces, leading to potential dermal exposure. Other hazards associated with vat photopolymerization include non-ionizing radiation. Sheet lamination materials include metal foil, polymer films, paper, and adhesive. Other hazards include non-ionizing radiation and ultrasonic noise.